All right, this is chapter 2, part 2. We left off last time talking about the linear model. Um, and just to refresh your memory of what that looks like, here's what that linear model looks like. According to this model, the impact of the independent variable, which I will, throughout the semester abbreviate with IV there, independent variable on the dependent variable changes at different levels of the independent variable. So an example would be that each year of school makes that should say huge difference at low levels, but less of a difference at higher levels. See, so just imagine if we go back to this curvilinear one, imagine instead of this being a graph of BMI and percent fat, and let's say that it was education and income. And so you could see that at the low levels of income, over to the left-hand side of the chart, an extra year of school gives you a big boost in income. That curve, that line is pretty steep. But if this is how education and income actually work, you get less benefit, less bang for your buck on education as you get to the high end. So over on the right-hand side, when you have highly educated people, yes, you're still making more money with each additional year of school. That curve is still going up, but it's flatter curve, which means that putting it in plain English, it means that that extra year of school is not going to make that much of a difference in your income. It'll go up a little bit, not a lot, but it makes where education makes a big difference according to this kind of model would be at the low levels. It's very important to get from 11th grade to 12th grade because graduating from high school is going to give you a big increase in income, right? So 1 year when it's 11th to 12th grade is really important, but 20 years to 21 years of school might not make that much of a difference, might not give you that big of a boost. So that's curvilinear. The impact of that independent variable here, education, the impact is different at different levels. That's what curvilinear is all about. Now, while the statistical models in this course seem complicated and varied, and you'll see that as we go through, if you were to glance through all the chapters, you're like, wow, this is a mind blower. And they can be challenging, but again, we're going to do the best we can to simplify and put things down in plain English as much as possible. But one way to look at all of the different models that we'll cover this semester is that they're really only just kind of, they're can be reduced down to a couple components here. And that is that you have a model, think of that line, that predicts the outcome, that's what the whole goal is. We want to be able to, based on the independent variable, let's stick with the education example. Based on your educational level, we come up with a model that predicts how much money you're going to make. That's the outcome based on that education. But since that line, all those dots on that graph are not going to fall on that line perfectly, that there's going to be what's called some error. And that we can think of error as the difference between what the model predicts that where you're going to end up and what the truth is, what your actual level is. So I want to stick with this linear model here, which is closer to what we'll be doing all semester. But again, let's say that this is education and income is what the two variables we're looking at. And so your up and down is that your education is this level. And so according to this line, your income should be straight across from there. Your income should be like this level over here, straight across from that line, right? Straight across from the line over here. Then you see what your educational level is. But let's see this person right here. See this person right here. This person, the model says that their income should be down here where the arrow is. But actually, their income is way up here at this level, straight across. Remember, we're going straight across, either straight across or straight up and down. So this person makes more, than their model, than the model says they would. So the difference, you got to think of error as the difference between how much money they actually make here and how much the model says they're going to make, which is right here. That gap between this point and this point, that's the error. It's how much the model is off from the truth, from the reality of how much you actually make. And that, let's go back to that point here. See, you see that the model predicts that you're going to make a certain amount of money, the outcome. But it's going to be off a little bit. So you got to add in that gap. There's going to be some error. So the amount of money that you make is equal to what the model says you're going to make, but then add the error, because chances are what the model says will be off a little bit. That line's not going to hit the dot exactly. And so there's going to be a little error there. So you add the error, that gap, to what the model says, to the line, what the model says you're going to get. You add those two together, and that gets you your actual, how much money you actually make. All models are like that. They have all equations are like that. You have the line, you have the error, and together those will tell you what your outcome is, what's your dependent variable. With this example, how much money you're making per year, sticking with that example. So think of it like that. Think of it in these different parts. You got the model, the line, the error, the gap, and what your results actually are, the outcome, the dependent variable, how much you actually make. Now, a couple other terms you've learned, I'm sure, in previous classes, but let's review. This is really important that we lay this out and that everybody's clear about this as we get going in this course, because I'll use these terms all the time, and you want to make sure you understand them so you know what I'm talking about. And textbook too. So we have this term population, which is also called universe, and this refers to the total group that you want your findings to apply to. It's the total universe, that the total group that you're interested in learning something about in your study. And I actually I believe I've got there's a visual that shows this population and sample part of it. So the population is just everybody that you're interested in learning something about. So, and that's really determined, that's decided by the researcher. The researcher is the one who decides, okay, I'm interested in this universe, in this group of people. Say, for example, it could be all current ISU students, undergraduate students, or graduate students, or both, right? It's up to the researcher to make that. We have this boundary here with this oval shape, right? Where that line gets drawn, where that boundary is, that's up to the researcher to decide. They could say, I want all currently enrolled ISU students. Or they could say, no, I want all currently enrolled college students all across the state of Idaho. That's going to be my population. It's up to you what that is. But usually researchers pick convenient populations, which kind of make sense, like, everybody in one city, or everybody in one school, or everybody in one, I don't know, kids group or something like that, daycare center or something, whatever, it's a million different things. But it's whatever the researcher decides, but it's everybody in that world, that universe, that the researcher defines that. The sample is the little segment, the sliver, the slice from the population that we actually collect data on, and that we actually analyze the data. We're not going to collect data on everybody, because the populations are usually too big and too difficult to reach everybody. If our population is the United States, if we decide that's what we want to learn something about the United States, well, there's 330 million people in the United States. That's a lot of people to sample. It's too many. And you see, if you pay any attention to surveys, polls of Americans, adult Americans, they usually poll 500 people, 1,000 people, usually not too much more than that, maybe 2,000 people. But even 2,000 people is a tiny, tiny little drop in the bucket compared to 330 million Americans. So the reason why we use samples is that it's impractical to collect data on everybody most of the time, especially if you have a big population. And so generally speaking, we're not going to collect data on populations. We collect data on samples. Samples are just a small percentage of the total. But you can see in this visual here that hopefully we want to get samples that look like the population. See, you see here in the population we have certain individuals that are red, we see some that are blue, we see some that are white, some that are male, some that are female, and then we want to have a sample that reflects that mix, reflects that combination, because samples are supposed to be a mirror image, an accurate microcosm. Think of it as like a mini world of the big universe, and an accurate one. So it's important. That's something we're not going to stress in this class too much. Well, we will in certain contexts, the representativeness of the sample, whether it's a biased sample or not. But that's certainly something that's stressed a lot in research methods, because you're not going to get good results from your sample if your sample is not reflective, if it's not representative of that total population. Because even though we're only collecting data on the sample, what we're interested in learning something about is the population. We're not really interested in learning about the sample for its own sake. We're interested in learning about the population because that's our group of interest. That's what we're after, is we use the sample to tell us something about the entire population, the universe. That's what we're interested in. We use the sample with that goal in mind. And here you see I've got the sample defined as well. This is the slice of the population that you actually collect data on and analyze data on, which is what we do in this class, analyze it statistically. And it's also, the sample is also what you want to use to generalize to the whole population, to be able to draw conclusions about the entire population. So an example of that would be, let's say you wanted to learn about what students' attitudes were on campus, ISU students, with respect to say COVID-19 policies. Do people want to have, say for example, do people prefer seated classrooms? Do they prefer doing Zoom meeting sorts of classes? Do they prefer fully online recorded lectures like what I'm doing right now? So if we wanted to get the campus's students' true attitudes towards what type of classes that they like in the middle of this pandemic, well, we would get a sample and we would collect the data for that sample of people, and then we'd analyze that data. But we're not really interested in our 100 people, for example, that we sample. That's not our goal. Our goal is to use the information from that 100 people to generalize, to learn something about the whole campus, which is over 10,000 students, right? So just keep in mind that's the population and sample are closely connected, but you should understand the difference in what we're trying to do here. The reason why we don't study populations is that most of the time they're just too big and it's not practical to interview, over 10,000 students on campus. So it's the practical thing to do is take a little slice, but pick one carefully, a slice carefully, so that it's basically looks the same and is made up of a cross section of people, which matches very closely, hopefully perfectly as possible to everybody, to the whole population. Parameters. Now there's a couple more fancy terms. A parameter is a statistic that's based on the whole population. So this is more theoretical because we usually don't get parameters. We don't calculate parameters because we don't have information on the whole population. So let's stick with the United States as an example of our population, 330 million people. Yes, we do the census every 10 years, but even with the census, we miss people. So even the census is really kind of a sample because we're going to miss a few. And if you miss even one or two people, you don't really have a census. Census means everybody. You have a sample. You might have almost everybody, but it's not 100%. So this parameter thing is really theoretical because generally speaking, we just don't have data on the whole population. But still, it's important to kind of talk about parameters because it helps our understanding to engage in this theoretical kind of discussion. So parameters, when we use that term, that just means a statistic like a mean that would apply to the whole population. So if we, for example, mean age of Americans, right? If you could somehow realistically get data on every single American, their age, and then you calculate a mean for over 300 million people. And let's say you get a mean of 40 years old. That's the average American is 40 years old, right? That's the mean average. Okay, that mean average is a parameter because it's based on the data from the entire population of the United States. Again, this is theoretical. It doesn't happen in real life because we don't get data on every single person. You know, it's just not practical. But whether you're talking mean, median, mode, standard deviation, all those range, all those statistics that we talked about last time, those are called parameters if they are calculated on data from the entire population. Okay, parameter. That's what parameter means. Estimates, on the other hand, this is the term for statistics that are based on the sample, which is what we work with day in and day out, is sample data. So let's go back to that ISU example. I sample randomly 100 ISU students and ask them about their attitudes about what kind of classes they like. Then I calculate, say, like the mode. What's the most popular class that people like the most? And it turns out that people like the video recorded classes the most online, most convenient, least complicated, and also they don't have to worry about going to class and dealing with all that. So let's just say they like that one. So let's say that 50% of the students surveyed say that's their favorite, right? Okay, that's a mode, remember? That's the most popular answer. So since that mode, let's say is 50%, is based on a sample, 100 students, that's an estimate because it's estimating what the favorite class is for the whole campus, which is over 10,000 students. But since we don't have data on every student, we only have time and money to collect data on 100 students. Okay, that's a sample, and the mode that we calculate on that sample, on that data, that mode is going to be an estimate. It's not going to be a parameter because it's not for the whole population. So estimate, that's a great term because it tells us right in the term itself that it's an approximation. It's not perfect. It's not a parameter. It's not exactly right for the whole population. It's going to be off a little bit because it comes from a sample, and samples are not perfect. We want them to be a close approximation to what the population looks like, but they're generally speaking not going to be perfect. They're going to be off a little bit. So the estimates are going to be off a little bit. And that's okay. We're just trying to get as close as we can. Statistics is not the art of perfection. It's just trying to be as close to the truth as you can be. Okay, so let's see. Let's stop there where this part's gotten plenty long. We'll continue on later.